All right. So today I'm going to talk about building a data-oriented future. I want to give you a little bit of background about me to start with, why I'm here. So I've been working in games for about 25 years, mostly in the console AAA space. So I've done PlayStation 1 games, PlayStation 2 games, PlayStation 3 games, PlayStation 4 games, Xbox 360, Xbox One. The last game that I worked on after about 11 years of being the engine director at Insomniac Games was Spider-Man. So from a career in working in the engine space in game development, I moved to Unity, where I no longer directly work on games. So the question is, why? For me and my journey. So Unity reaches so if we look at over the last 12 months, about 3 billion devices have run made with Unity experiences. About 29 billion installs of made by Unity experiences over that same 12 months. In about 192 countries, there are developers working in Unity. And in the last 12 months, there have been over 2 million active students learning in Unity. About 45% of the top 1,000 mobile games are made with Unity. 50% of all new mobile games are made with Unity, and about 60% of all AR and VR content is made with Unity. About 60% of the content at Tribeca Film Festival made with Unity. 65% of the interactive content at Sundance was made with Unity. And of all the most innovative AR and VR companies, as defined by Fast Company, they're powered. 90% of those are powered by Unity. Unity supports 25 platforms, or a little bit more. So for me and my journey, Unity meant impact. So what's my mission, and why do I want to reach that group? There's two things that I want to accomplish. One is I want to see a future where players get the maximum value from their experience when they're playing. So if there's an app here for this conference, right? And there's a sort of a stream complaining about the app from this conference. And my battery's being drained and it's using too much data and all the things, right? That's not you feeling like you're getting the maximum value from your experience. That's precisely the kind of thing that I want to personally address. And I want enough game developers, or just developers in general, capable of fulfilling that promise. Right? I want the world to be full of people who can do a good job with that and make sure that every player who picks up their phone, is playing a game or using an app, feels like they're getting the maximum value from that experience. So that's my personal mission and why I'm here and why I'm at Unity. What I do at Unity is lead our data-oriented tech stack development. What we're focused on is, which we call DOTS, which we focus on high-performance, multi-threaded, scalable, and optimized code. And delivering that in a way that our users, our developers, can achieve the same thing. So what problem are we trying to solve? So I like to say the problem we're trying to solve is get the clowns out of the car. If you're trying to race a car, you're trying to race this car, for instance, the problem is not how fast the engine is. The problem is not how streamlined the car is. The problem is that you have a dozen clowns inside holding it down. So before you do anything else, you need to get those clowns out. And that's what I'm focused on. The most obvious, the biggest problems that we have, the lowest hanging fruit that is just holding everybody back. So the problem is, as I see it, that the default approach that we teach just for engineering in general is terrible for performance. The default approach is also not optimizable. You get to a wall and there's nothing you can do. There's no fixing it. The default approach introduces problems and complexities and additional machinery, more complexity than you actually need to solve the problem. And the default approach on top of that rarely solves the actual problem. So I like to say there are three big lies in software development. Most of the time I talk about this in terms of what's wrong with object-oriented programming in particular, but it's just three lies that are prevalent in the engineering industry as a whole, and certainly also in game development. One is that software is a platform. We teach people that software is a platform, that you can reason about software independent of the hardware, and that's simply not true. There's no world in which that's true. Software is not a platform. Two, the second lie is that code should be designed around a model of the world, that you should have this model of how the world works, and you should be telling the story inside your code and ignoring the realities of both the hardware and the data. That's also a lie, because there's no world in which that produces good engineering results. Now, third, and sort of really insidious thing that we teach our students is that code is more important than data. We teach them how to code. We teach them what code is like. We teach them syntax of code. And what we don't teach them is what's important about the data that they're transforming, what the most important thing that they should be looking at is. So these three sort of insidious lies have crept over decades into the industry as a whole, and have gotten us and dug us a giant hole that we now have to get out of. So what do we want? We want performance by default. We want the default thing that you do to approximate the right thing, to approximate something that's performant, and will get you there. We want optimizable by default. So if it's not optimized right out the gate, if it's not the fastest thing it could possibly be right out the gate, that's fine, so long as there's a path for you to get there. Because too often, you're put in a position where you write something and you've painted yourself into a corner. There's in fact no way for you to get to an optimized version of that. So you might hear somebody say, well, I'll just measure this at the end and I'll fix it. There's in real production, in real life, in real engineering, you can't just do that. There's no fixing it right at the end. One, the scope of those fixes are much, much too large for the cost and risk at the end of a production. On top of that, half the time, you just need to throw everything away anyway because you designed it wrong. So two things in terms of optimizability that I want to solve for. One is I want to have no pre-production and production wall. So there's a common theme that I'll hear where people will go through pre-production, and certainly in game development, but in other developments as well, where they'll build something to see, how it's going to work, right? This pre-production. Is this going to be fun in terms of a game, or how are these mechanics going to work? That's pre-production. Answer those questions. And then they want to transfer from that pre-production work or that prototype work to production. And the only real answer they have at that point is to throw all that away and start over again. What are the lessons that we had and start over again. So it's this wall between pre-production and production. And what I want is an iterative experience. You get to that end of experimentation and you can take that and actually use it to continue on your development path. And I want no paratroop optimizers. So certainly in games, what we see is that there's a sort of group of engine programmers, generally speaking, at any given studio, that right at the end of development will try to go in and fix everything up. We'll try to go in and optimize it down to under 16 milliseconds or under 32 milliseconds, depending on if they're running 60 or 30 frames a second. They'll try to sort of squeeze all that stuff right in at the very end, and it's very difficult. It's very difficult to do because they can't make massive high-risk changes, and there's a limited number of people that can actually do this work. I want scalability by default. So one of the things that we're focused on is moving from, is looking at games that are as small as 100 kilobytes to games that are as large as 100 terabytes. So I want those choices to be available to developers, but I want to make sure that we've covered that range. And I want the fewest number of moving parts that will solve the problem well. So one of my goals is to help developers understand their actual problems and help them solve them well. So I want to make people, as they work with what we're doing, understand their own problem better. And I want to coexist with experts. So what I don't want is a world in which we're providing a solution and you don't have to think about that thing anymore. It's not a black box. What it is a utility. It's a thing that you can use, and you can focus on which parts of that you want to use. And if you are an expert and you can do some part of that much better, we want to coexist with you. We want you to be able to replace that part and do it much better. So what is the core tech that we're working on? So one is a job scheduler, a job system. So how we go multi-threaded by default. Everything that we do should be multi-threaded by default. One of the things that we've seen in games in particular is they're blocked on the main thread. You have most of the work happening on the main thread, and then occasionally you'll be able to to push things off onto other threads or other cores. This is a systemic problem in design where you've designed something to be sequential initially, and there's no way out of that space. So we want to make it by default, it's able to go wide. Part of our core tech stack is a burst compiler, which I'll get into a little bit. It's a new compiler around a new language called HPCSharp. Our memory containers, and ECS. So I want to talk a little bit about what I mean by ECS in our context here. But first, let's talk like the sort of big picture of how all these pieces fit together. So you have your game or application. Under that, you can use a set of packages. Some of those may be ours. Some of those may be from other developers. Some of those may be your own. One of those packages is ECS. Those all, by default, run wide across all the cores available on whatever machine that you have in jobs. We have a job scheduler that works with those. Our native containers, which is the thing that allows you to reason about memory. And our dots runtime. The burst compiler is a thing that knows across the stack and will compile the code so that it works with all of this. So how does the job scheduler work? First, the critical thing is that you have to fully declare the data used in any job. There's a critical portion of being able to reason about what data is being accessed. You have to tell us what data is actually being accessed. There's no arbitrary memory access in a job. You cannot optimize that if you do that. You have to declare read-write permissions on that data. With those two things, we can do verification of correctness. We can tell you if there is a race condition, and we can have you fix it. This, in terms of actual practice, it makes a massive difference. When we look at where game developers in the industry is in general versus what this allows, is multi-threaded coding in particular tends to be an expert level practice. When you want to optimize for that, you tend to need experts in that space. So what having the ability to give you feedback on correctness gives you is that anyone now can start to experiment in that space. If you do it wrong, we'll tell you you're doing it wrong. So you can trust say a junior programmer or somebody without that specific experience to start working in a multi-threaded space by default and get the feedback of where they're doing it wrong and iterate and start to learn how to do it correctly. And that enables just about anybody to write multi-threaded, good, solid multi-threaded code. We also have overrides for special cases in those cases where you, as an expert developer, know what's better. We do, for instance, type-based alias analysis, and if you happen to know that these things cannot alias, you can basically cut through it and say, just let me do this. So for that, I've kind of heard it described as a sort of baby Rust. In the way that, we need to declare all these things, we need to declare these connections so that we can do verification, and that way is the same. However, because we let you sort of cut through that when you absolutely do know what's going on, it's a little bit different. So I'm going to talk about our burst compiler. Why did we choose this HPCSharp, which is a subset of CSharp? One is that CSharp is already familiar to Unity developers. About half of all CSharp on Earth is in Unity. So it's a significant part of the ecosystem. HPCSharp is a reasonable subset of CSharp. This is not an issue of CSharp versus native code, because that's not what we're doing. HPCSharp is native code. We have a compiler, it's compiling it to native code that's specific to your platform. So it's a full compiler, actual ahead-of-time compiler. So what is that subset of CSharp that we're talking about? So it's constrained by having no class types. Anything that would garbage collect, out the window. Anything that is garbage, out the window. So no class types, no boxing, no garbage collection allocation, no exceptions for control flow. And what these tighter constraints give us is a highly optimizable language that we can compile ahead of time, and we can statically analyze your code for safety issues. It's still C#-ish. We have all the basic types. We have structs, enums, generics, properties. It's a safe sandbox, even for parallel code. So you're writing C#-ish code in parallel. Why didn't we just fix C#? So that's an intractable problem. By design, it's poorly designed for this case. Garbage collection is not a tractable problem. Manage objects mean cache misses, end of story. There's no way around this. Boxing is bad. and just tons and tons of object-oriented legacy code that is not optimizable. So instead, we focused on the subset of C# that we can highly optimize and that we can make guarantees about for our developers. So how does burst actually work? So we compile assemblies, and normally, as you're working it, as you're iterating, the assemblies get compiled normally using the normal C# compiler, since it is a subset of C#, and then asynchronously, burst compiles the job kernels in the editor. So it'll immediately start running in the regular C# environment, and then burst will compile it asynchronously. So burst consumes .NET IL. It's an LLVM front end. Because we can do alias analysis on our memory, we can run much more aggressive LLVM optimizations. We can get actual reasonable results at the end. And the ahead of time workflow will integrate with IL to CPP, which is our C# to CPP conversion utility. All of these job kernels can be pre-computed and pre-built ahead of time. And our in-editor inspector looks like this. On the left is all of the job kernels that exist in your game or project, and you can examine the assembly output, the IR output, unoptimized IR output, any state of that. You can also examine it per. You can change the compile options, and you can also examine it per target. So if you want to see what the assembly output looks like for ARM versus x64, you can do that. So in our view, burst in Unity is a better combination. We can do, right now we have some context-aware alias analysis. And by context-aware, I mean we know specific things about what your code is doing because we have an integrated top-to-bottom environment. So we know how you got that memory by using our memory containers. We know those memory containers cannot alias. So we can, in fact, insert that aliasing information and push it down to the compiler. We also want to introduce a lot more static analysis, offline analysis, and that's still unimplemented, but we're working on it. We're also adding precision and determinism controls. So you can say, I want much reduced precision in, say, these math libraries because I can afford to be sloppy, or I want much greater precision. We also want determinism. Not only determinism on the same platform, so if I'm running on x64, and I'm running another machine on x64, I expect exactly the same results, but cross-platform. So if I'm running on an ARM device, say my iPhone, and I want a server running, and I want that server to produce exactly the same results as my ARM, then we're going to guarantee determinism across these two devices. We're also going to introduce higher-level SOA to AOS conversions, so structure of arrays to array of structure conversions. This is normally a super manual process for programmers. Excuse me. A super manual process to redesign the data and transpose it based on a case, on your specific case. And so what we're trying to do is introduce the concept of you could just transpose that data with a switch and experiment with what's the best possible layout for you. And with all of this, we get Unity code iteration times. So as you're editing your HPCSharp file, it gets put into the editor, it builds, it runs, all of that. It's available inside the editor. It's available, and part of your iteration loop, and our target is under 500 milliseconds. So there's no long build wait times. There's no big link time for me to see the result of that in my editor. So our memory containers, as I mentioned before, no garbage collection. They're we support custom allocators for common use cases like temp and temp job with lifetime and access rules. The key to our memory containers is that we have good aliasing rules by default. By default, we're saying these containers cannot alias. That's understood by the compiler, and therefore we can spit out that information to LLVM. Therefore, it can give us actually good results at the end, which is something, if we compare to, say, C++, something that's not possible in that scenario where you have an unknown source, the compiler doesn't know where that memory came from, cannot do an aliasing analysis based on two separate pointers, doesn't know that they could possibly not point to the same thing, which is why, say, the restrict keyword was introduced. However, there's no possible practical way for you to introduce restrict across your entire application anywhere that could possibly poison that data. We can do that. So what does ECS bring us? It brings us a good, for ECS, we want a good default data layout. We want a good default transformation pipeline. We want a good data iteration experimentation workflow, and we want it to be optimizable. So a quick background on what ECS is. So in sort of typical object-oriented space, you have game objects as a container. It's a class that has a bunch of stuff in it. And it looks like this. They're each individually heap allocated. You can imagine each one of these is an individually heap allocated game object of various pieces of data, and they're just all over memory. ECS is different in that an entity is just a key into data where the data is homogeneous of a specific single type. So it looks more like this, where each one of these things is a set of types, and it's a structure of arrays, basically, of the individual component types. So if we look at this and divide it into, if we look at this, each of our types here, divided into separate individual chunks, what we call an archetype is the definition of the combination of specific components that you might have. So an archetype is a set of types. Like if you have position, rotation, render type, and a rigid body type, that's what we call, that combination is what we call an archetype. Chunks are currently a 16 kilobyte block of memory, structure of arrays of all the types that you have in that particular archetype. We have a concept of a query, so you can request a specific set of types. So I'm requesting these two colors, for instance, and it says these are all of the archetypes that match those two colors. It can gather them up, gather up all the chunks that belong to them, bring them all together, line them up, stitch them together, so that you can process a work kernel across the specific types that you've requested. And that work kernel runs inside of a system. So basically the two concepts that we have are the components and how the components are laid out in memory, and the systems which run across those queries. We have worlds for isolation. Conceptually, this is how a job component system works. You basically are launching, you have a management thread, which is the equivalent of your main thread, which launches a bunch of systems, and each one of those basically by default goes wide across as many cores and worker threads as you have on your machine, and those all get stacked up. So let's talk about, that's the background of what we're doing. So I want to talk about what are the principles behind what we're doing, and a little bit about what data-oriented means. So what are the principles of data-oriented design? So first is the global energy required to transform some data should be proportional to the amount of surprise. And what that means is how much, if you have an event that's not surprising. So for instance, if you have a frame in a game, this frame and the next frame in the game. The next frame is guaranteed 99% of the time to be very, very similar to the previous frame. Most of the work that you do in the next frame is unsurprising. So it should be proportional to that fact. You should be, in fact, doing less work in order to provide that second frame. By comparison, if the camera had completely moved across the world, right, then the second frame would be completely unrelated to the previous frame and should be doing more work in that case. So it should be relative to what's surprising. So as an example, like think about where you keep your toothbrush. It's unlikely that you keep it in a drawer in your kitchen, right? Most likely scenario is that you keep your toothbrush next to your bathroom sink. Why do you keep your toothbrush next to your bathroom sink? Because it's unsurprising that you're going to have to brush your teeth. You know for a fact that you're going to have to brush your teeth tomorrow, tonight, whatever. So you prepare it and you put it very close to the place where you know you're going to have to brush your teeth. So the amount of energy you need to put in to get your toothbrush is proportional to how surprising it is that you're going to need to brush your teeth, right? So the opposite of that would be you store your toothbrush under your bed, right? And every time you want to brush your teeth, you have to go get it. But the fact is that that's how we program. That's how, by default, we program. People put their data in a place that's far away in terms of it's not in cache or it's in memory, it's on disk. They put their data in very far away from when they actually need it, even though they know they can guarantee that they need it. And when I talk about global energy, I'm looking at it, in fact, globally. So I'm looking at our Unity work at Unity, times the number of developers using Unity, times the players that are playing those developers' games and applications, times the time that those play sessions are happening. So all of that energy, actual energy usage, practical energy usage, whether that's energy being pulled from this power cable on my laptop, or it's on a battery on device, all that energy adds, everything impacts that energy usage. And I would like to reduce that. So the next principle is the purpose of all programs and all parts of those programs is to transform data from one form to another. This should be intuitively obvious. A computer literally cannot do anything else, right? It gets inputs and it gets outputs. A game is basically an input and output machine. There's controller inputs and the output is the screen and the audio. And it's hierarchical from there. Some piece of that is inputs and outputs and does something. Some piece of that is inputs and outputs and does something. That's literally all a computer can do. And yet somehow we're taught to do something different. We're not taught to transform data and understand the transformation of the data. What we're taught is to tell a story with code abstraction. And that's not what we need to accomplish. What we need to accomplish is transforming that data with the least amount of energy that we possibly can. But let's talk about abstraction a little bit. So there's two kinds of abstraction when I think about abstraction. One is utility abstraction. So this is scaffolding. So this is, I'm giving you a tool to do something, and you could use that tool or not. So for instance, a light switch in my house is utility abstraction. I could not use that light switch. I can take the light switch off and I can wire those two wires together, and that's fine. It's not actually hiding any information. It's just making it more convenient for me to do a specific activity. Then there's a second kind of abstraction, which is storytelling abstraction, where in fact I am trying to hide what's happening with the data, where I am trying not to inform you about what's happening behind the scenes. And between those two things, one of those is useful and good, and the other one is really, really not. The next principle is that if you don't understand the data, you do not understand the problem. So in terms of understanding the data, imagine that if I say, I'm going to give you a deck of cards with integers on them, and I want you to sort them, or I want you to add up the numbers on these cards. And you can think about how you might do that. And then I say, okay, well, what if there's only 10 cards? How would you approach that problem? What if there's 1 million cards? How would you approach that problem? What if there's 10 billion cards? How would you approach that problem? What if 99% of those cards were 0? How would you approach that problem? Almost all of those questions, all the answers to all those questions would be different, completely different. In fact, in each one of those cases, you're talking about essentially unrelated problems, that the solutions would have very little to do with each other. Even though the mechanics of adding or sorting are similar, the actual problem solving is very, very different. The solution looks very different in those cases. So you need to understand the data, or you simply cannot solve the problem. And conversely, you need to, in order to understand the problem, you can inspect and understand the data. And this is trivially demonstrable in any code base. Pick any function in your code base and capture the data in it. Dump it out. Look at it. Actually examine it. There's inevitably something that you can learn from that. Inevitably something that's going to surprise you. Different problems require different solutions. Programmers love 3 things, in my experience: generic frameworks, platform independence, and future-proofing. No. Let's say no to these things. So generic frameworks is implying that I don't want to know anything about this problem, and I want to hide all the things about this problem. And in fact, not only do I want to do that, I want to kick it down the road for somebody else to solve. And you're not actually going to solve the problem. So what I don't want is generic frameworks. What I want is utilities and standards, things that people can actually use. Platform independence is not a thing that actually exists. You cannot be independent of the platform. That makes no practical engineering sense at all. What you have, though, is platform commonalities. You have some platforms that are very similar, that share similarities, and you can combine those similarities. That part is fine. Future-proofing is another example of something that doesn't actually exist. You cannot future-proof. You cannot solve a problem that you can't possibly know what's there, what anything at all about that problem. So you need to solve problems that you actually have, or that you have the experience to anticipate. There are problems that you can anticipate. Those are fine. And I'll add this tweet. The only future-proof systems I've seen are systems that are easy to delete, which I heartily agree with. If you have different data, you have a different problem. So if you catch yourself thinking, I'm looking at a problem, well, what's the best way to do this? Generically, abstractly, you're thinking about that. The answer is inevitably, there isn't one. And what are you measuring? And you need to stop, and you need to, if you catch yourself saying this, you need to stop and look at your data, because that's going to help you answer your question. There isn't a best way abstractly. There's no abstract version of this problem. You need to actually look at your data, actually examine it, and that will help drive what the actual solution is. If you don't understand the cost of solving a problem, you don't understand the problem. So if I'm sitting down, I'm saying, okay, I have a problem in front of me and I'm trying to solve it. I'm trying to create a system, or I'm trying to create a feature, and I'm trying to reason about how this feature is going to work. But if I haven't thought about what the cost of doing it is, then I can't possibly understand it well enough to solve for it. And there are 4 things in particular that we reason about that I think every problem needs to reason about, and that we want to build tools to help people reason about. One is performance constraints. If you're not reasoning about what the performance constraints of any problem you're working on are, you're not solving the problem. You simply cannot solve the problem well. So whether or not it has to fit in 1 millisecond or 10 milliseconds or 10 minutes, it doesn't matter. The fact is that it has constraints. So whatever you're thinking about, whatever problem you may be working on, if you think, well, I haven't thought about the performance constraints of this problem, then you think, well, it doesn't really matter. For whatever I'm working on, the performance doesn't really matter. That's, in fact, never true. Because if we took whatever you're doing and we said, I'm going to multiply by, it's going to take 10,000 times longer to do it. We're like, obviously, that's not good enough. Like, obviously, it has to be faster than that. Okay, well, then there is a constraint. What actually is it? Find that number so that you can stay under it. Second is determinism constraints. Do you want to make sure that this thing is repeatable? Scalability constraints, how big, how small, how many? And workflow constraints. UX is part of designing a solution for any problem. If you don't understand the hardware, you can't reason about the cost of solving the problem. So this is what I mentioned. There's no such thing as a software platform. That makes no sense. Everything that you have runs on some hardware somewhere, and you have to be able to reason about what hardware it's running on, at least at some level. And so somebody might say, well, it's obvious. It's obvious it's going to work. It's obvious. It'll be fine. Well, is it true? Is it truly obvious? Like, is whatever you're working on going to run on an NVIDIA GPU? Will it run on an ARM device? Will it run on a Pico 8? Will it run on 10,000 distributed x86 64 cores? Will it support SSE 4.1? Will it run on the iPhone or on the Android? These are all platform and hardware questions that must be answered as part of designing any piece of software. So can the compiler figure this out? Can I just do whatever? Well, let's talk about some specific case. The answer is no, but let's talk about some specific issue around a common x86 64 core. So if we look at what people normally would consider expensive, which is a square root instruction, it's somewhere in the range of, say, 20 cycles on a very fast machine. But if we look at the actual memory access times, what we see is it's basically 3 cycles-ish to get data from L1, up to more than 200 cycles to get stuff from main RAM if you have an L2 miss. So what does that look like? So if I have something in memory versus something that is an L2 miss. So L1 in L2 in L1, great, fast. In L2, not as fast. And if the memory I need is not an L1 and not an L2 and I need to go to RAM, what does that look like? Right. So L2 cache misses per frame are very likely to be your most significant component, the most significant thing that you need to concern yourself with as an engineering issue. So let's take a really quick example. Imagine this is a game object, or a game object like this that has some function, the method like this, which is just multiplying a couple of things. And imagine this is heap allocated in a very traditional object-oriented way. So what does that look like? Here's the code of that function. What we see is, you see a 2 by 32-bit read here, which are, let's say, are on the same cache line. It takes about 200 cycles. We do our floating point mul and add, which is about 10 cycles. Let's assume that the square root is in line, and that's about 30 cycles. And then we do our multiply back to the same address, which is now an L1, so let's say it takes about 3 cycles. And then we read and write the new line from the next line, which takes us about 200 cycles. So the point of that, looking at that, is the time spent waiting for L2 versus doing actual work in this function is about 10 to 1. That 1 is the compiler space. That 1 is the space the compiler can fix. So if we look at it a different way, This first line, we wasted 56 of 64 bytes. You're reading in cache lines. There's no way around it. That's how the hardware works. We wasted 56 of those 64 bytes in that read. If we look here, we wasted 60 of our 64 bytes in the next cache line that we needed to read, which amounts to about 90% waste. This is waste of actual energy and actual things that are actually happening on the hardware that we're dealing with, which means everything, by nature, is about 10 times slower than it needs to be, just for doing nothing. So you can also think of it as 10% capacity used. That doesn't actually mean 10% used well. On top of that, there's additional optimizations that can be done. But this is pure, these are the clowns in the car. This is pure 90% waste for no value whatsoever. And this particular thing is why we have organized our data in this format, in this structures of arrays in chunks, so that by default, things are getting loaded in this form. Everything is a data problem, including usability, maintenance, debuggability. Everything is a data problem. Measure it, figure out what you want to improve. So what we want to do is give everyone the tools to understand what they're doing and fix mistakes. We want to help build experts, not replace experts. And solving problems that you probably don't have creates more problems you definitely do. So this speaks to building abstractions. Every abstraction you make is another set of problems for somebody else. Like, you're going to invent something else that now somebody else has to understand, and they have to understand all the edge cases and all the weirdness that you've created as part of your abstraction. On top of that, they have to understand the thing that the abstraction sits underneath. And on top of that, they have to understand the hardware. Every abstraction you create creates problems. So you need to minimize the actual abstractions. The more context that you have, the better you can make a solution. So, for example, Burst has context about where memory is. That's the advantage of Burst. We want to help developers build tools to take advantage of what they know and we can't know. So, overall, what I want to talk about when I mean data-oriented design is it's not magic, it's engineering. We want performance by default, and we want optimizable by default. Thank you.